So let's see. We were talking about crystallographic root systems. So we talked about how, well, to any root system, you can associate a Cartan matrix. And the way this looks is that it's a matrix whose rows and columns are indexed by the simple roots. And in the entry alpha comma beta, what you write down is the inner product of alpha and beta check. Where, remember that when I put a check, I'm just renormalizing the root. And the way that I do it is that.
Excuse me, can I borrow a pen or pencil from somebody? I just ran out of ink.
So beta check is this normalization of beta. Now, I don't know if you noticed in the last class, I was a little confused for a while because my notes were not matching what I was remembering, and I was right that my notes were wrong. And last time I put a minus sign here, but that minus sign should not be there. Okay? So I fixed this in my notes, and I'm going to upload my notes again correctly. Just be careful if you watch the lecture. I have minus signs where I shouldn't. Okay? So beta check is beta multiplied by 2 and divided by the square of the length of beta. Okay? And we talked about how actually with the Cartan matrix you have all the information. So if I give you the Cartan matrix and I give you the simple roots, then you can recover all the roots. Okay? And we were talking about how basically if I want to classify crystallographic root systems. So when is it crystallographic? It's crystallographic when all of these numbers are integers. Okay? So crystallographic if these are all integers. And so then, if I want to classify crystallographic root systems, that's going to be basically the same thing as classifying Cartan matrices which are made of integers. So integer Cartan matrices. And this is our next goal. Our next goal is that we want to understand when, if I give you some matrix of integers, when is it a Cartan matrix? Okay. So this is our next goal. So let's talk about some necessary conditions for Cartan matrices. So some necessary things. First of all, what are you going to see in the diagonal? In the diagonal, you're going to see the number alpha comma alpha check for each root alpha, right? And if you go ahead and compute this, you're going to find that this is alpha comma alpha check is 2 alpha divided by alpha comma alpha. And then you find that, so again, this is bilinear. You can pull out the 2, pull out this denominator, and you find that this is just 2. Okay. So that means that in the diagonal, you're always going to see 2s. Okay. What about off the diagonal? Well, off the diagonal, what we're going to see is something that looks like this. And after renormalization, this looks like this. But then if you remember, there's two facts about the way that the simple roots interact with the inner product. First of all, we said that all the positive roots, all the simple roots have inner product with themselves, which is positive. And second of all, we said that two simple roots that are different have negative inner product. The way that I talked about it is that if you are in a Euclidean situation, then the angles between them are always obtuse. What this means then is that you're always going to get a negative integer. Okay? So on the diagonals you have 2's. Off the diagonal you have negative things. Well, actually, what we proved is that this is less than or equal to 0. And just one last thing, which is that if you have that alpha beta check is 0, then what happens is that alpha comma beta is 0, which is going to tell you that when you do beta comma alpha check, that's also going to be 0. In other words, there's kind of a symmetric condition. It's not that this matrix is symmetric, but the positions of the zeros are symmetric. Okay? So zeros are symmetric. So these are some kind of immediate conditions that have to hold. Okay? But let's talk about what the full story is. So let me just tell you right away that this is not enough. So if you have a matrix that satisfies these conditions, you cannot yet conclude that it is a Cartan matrix. So here's a nice proposition that is going to be very useful. Let's suppose that you have a crystallographic root system. Okay? And we know that we have a corresponding Coxeter group. Corresponding Coxeter group. Okay? Now, this proposition is going to tell me if I tell you what the Cartan matrix is, then immediately you're going to know what the Coxeter group is. Okay? Then the Coxeter matrix of WS is given by let's call this delta alpha 1 up to alpha n. Okay? So that means that S is going to be S1 up to Sn. And of course, we know that if I want to specify the Coxeter group for you, all I have to tell you is the order of Si Sj, which we call Mij. So I'm going to give you a recipe to find out what Mij is. It's a very simple recipe. It says the following. Just multiply Aij and Abi and see what you get. Okay? What are you going to get? Well, one thing that we know about this number is that, if Ij and Ji are equal to each other, then if I and j are equal to each other, then this is 2 and 2, 4. If I and j are different from each other, then these are both non-positive, which means that when you multiply them, you get some non-negative number. Okay? So that means when you multiply Aij and Aji, then you're either going to get 0, or 1, or 2, or 3. Don't worry, I'll stop here, or more than 4. 4 or more. And my claim is that immediately you can tell what Mij is. If you see a 0, then Mij is 2. In this case, it's 3. In this case, it's 4. In this case, it's 6. In this case, it's infinity. Extremely simple. And strange. So what's worrying you, Andrew?
What's worrying me is over here, when I and j are equal to each other, I get 4 in the top one, right?
Uh-huh.
And I get infinity in the bottom one, which should be 1.
So let me say 4. This is true for I and j different from each other. If I is equal to j, then we don't even need to look at this because we know that mii is always 2. 1. Yeah. mii is always 1. So we only need to specify what mij is. Very nice proposition, I think. It tells you immediately how to read off the Coxeter matrix from the Cartan matrix. And it also starts to tell you that Coxeter groups that come with crystallographic root systems are special. Yeah? For example, any Coxeter group where you see an order of 5 or 7 or 23, there's not going to be a crystallographic root system that corresponds to it. Okay? So that's what we're going to prove. And I think this is a really fun proof, actually. This is applied linear algebra, I would call it. We're going to do some very nice linear algebra and get some nice combinatorics out of it. So, well, let I be different from j, okay? Now let's do one case already. So if what does it mean for Mij to be 2? Well, we know what that means is that Si Sj has order 2, or equivalently that Si Sj equals Sj Si. Okay? And if you look back at your notes from 2 classes ago, we said exactly when this happens. We said that Si and Sj commute if and only if. So this is if and only if. This is if and only if. What did we say? We said that either I was equal to j, in which case they commute for obvious reasons, because this doesn't really go if and only if. But this is true if and only if I is equal to j or alpha I and alpha j are orthogonal. That's what we proved. Okay. We're assuming that I is not j, and so it must be the case that alpha I and alpha j are orthogonal. Okay. Now, if you renormalize, this is still going to be orthogonal, and this is the number Aij. I realize now that I just started calling this Aij without telling you what it was. So Aij is the Cartan matrix. Okay. So A equals Cartan matrix. So this is the number that goes in the Cartan matrix. Aij is 0, which means that Aij, Aji is 0. Okay? So that means that if we're in this situation of having a 2, then we must have a 0, and vice versa. Yeah? Because if we have a 0, that means that either Aij or Aji is 0. Right? But then we know that the zeros are symmetric, so if one of them is 0, both are 0. And alpha I and alpha j are orthogonal, which means that Si and Sj commute. Okay. So what I'm saying is basically that in this case we understand. Okay? And we should focus on the case where the number is 3 or higher. Okay. So let's suppose that we have alpha, well, alpha I comma alpha j check is aij, which is A, and alpha j alpha I check is AJI, let's call it B, and let's suppose that Mij is at least 3. And let's figure out that this must go with how this table claims. Okay? So I want to look at Si and Sj. And I want to figure out what is this operation doing, because Mij is the order of this operation, right? So first of all, let's figure out what Sj does to alpha I and to alpha j. Okay. Well, for example, to alpha j, it's easy. Actually, let me just say it this way. So Si Sj is a linear transformation, or Si and Sj are linear transformations on the plane span of alpha I, alpha j. Now, they're linear transformations on the whole space, but in particular, they're linear transformations on the plane span of alpha I, alpha j. Why is that? Because what does Si do to alpha I? It sends it to minus alpha I, right? And what does Si do to alpha j? It sends it to alpha j minus, maybe let's write this, which will be useful. What does S beta of V do? Well, this is V minus 2 times V comma beta, beta comma beta, beta. And so this is the same thing as V minus V comma beta check, beta. Okay. So that means that Si alpha j is alpha j minus alpha I alpha j check alpha I. Sorry, the other way around. Alpha j alpha I check alpha I. So this is alpha j minus B alpha I. And so this is why Si is a linear transformation on this plane. It sends alpha I to the plane alpha I alpha j, and it sends alpha j to the plane alpha I alpha j. So really I can focus on that two-dimensional plane and see what Si Sj does to it. Okay. So on that plane, what does Si do? I can think of it as a 2x2 matrix, right, which takes alpha I and alpha j to this and this. Okay. So alpha I goes to minus alpha I plus 0 alpha j, and alpha j goes to alpha j minus B alpha I. So if I prefer thinking about matrices, then this is the matrix for the action of Si on this plane. And if I do the same thing for Sj, well, basically, it's going to look the same way, but changing the roles of alpha I and alpha j. So you just do it, and you see that you get this. Okay? And then what does Si Sj do? Well, what you do is you just multiply these two matrices, right? That's how you compose linear actions if you have matrices. So you multiply this and you get minus 1 plus AB, B minus A minus 1. Okay. So this is what Si Sj does on the plane of the span of alpha I and alpha j. That's the matrix. Okay. So that's what it does there. Okay. Now, what does it do to the rest of the space? And I want to understand what SISJ does. So this is what it does on here. What does it do on the rest of the space? Well, let me show you something, which is what's the dimension of the things that are orthogonal to alpha I? Well, what do I mean by this? I mean I'm looking for the vectors in this space that are perpendicular to alpha I according to this bilinear form. Well, if this was Euclidean, then it would be n minus 1. Right? And if it's not Euclidean, you should think about it, and you'll see that it's either n minus 1 or n. It can't be anything else. Because basically either everything in this space is orthogonal to alpha I or only dimension n minus 1. So again, if this is Euclidean, it's equality, and if it's not Euclidean, you should think about why it's more than equality. So this is a little exercise in linear algebra, and a good exercise. So then, of course, by symmetry, the dimension of alpha j perpendicular is also at least n minus 1, and that means that if I intersect these two spaces, well, if I intersect two things with dimension n minus 1, then this has to have at least dimension n minus 2. Right? This is given by one linear equation. This is given by another linear equation. And so if those two are independent, you get dimension n minus 2. And if not, you get higher dimension. Okay. Now, what's the point? The point is that here we have something of dimension n minus 2. Here we have something of dimension 2. And basically, there are complements. So what I wanted to do is understand what does SISJ do here and what does it do here. Okay. But what does SISJ do to things that are perpendicular to both I and j? Suppose that you have some vector which is here and here. What does that mean? That means that v comma alpha I is 0, v comma alpha j is 0. That means that what does Si do to v? Well, this is v minus this times something. So it says v. And what does Sj do? The same thing. V minus 0. Okay? And this should be no surprise to you, because what are we thinking about geometrically? We're thinking that we have, here's alpha I, our vector, right? Now, here's the plane of things perpendicular to it. What does this reflection do to things in this plane? Nothing. Reflections leave the orthogonal plane alone. So Si leaves this alone, Sj leaves this alone. And so if you're in both things, then both Si and Sj leave you alone, which means that Si, Sj just acts as the identity here. Maybe, just maybe, I'll try to draw a picture of what I'm talking about here. I'm a little scared of doing this, but let's try. The only way to overcome your fears is to just face them in the eye. I'm going to give you a drawing. Si is here, okay? Imagine that this is a three-dimensional picture. And Sj is here, so that means that here are the things that are perpendicular to alpha I. Here's alpha I. Okay. and V here are the things that are perpendicular to alpha j, and here is alpha j. Okay. So what am I doing? Well, this is the whole space V that I live in. Okay. Now, and let me assume that here we have equalities just so the picture makes sense. So alpha I is a vector, and so this black thing is a hyperplane, dimension n minus 1. Alpha j is another vector, and so this blue thing is another hyperplane, dimension n minus 1. And generally, they intersect in an n minus 2 dimensional thing. Okay? And so this line right here is crucial. This line right here is alpha I perpendicular intersect alpha j perpendicular. Okay? So I'm saying two things. First of all, that SI, SJ leaves things. Now here it looks like a line, but in general it's an n minus 2 dimensional thing. Okay? And this whole n minus 2 dimensional thing is alone. You just leave it alone. And the only interesting things that SI, SJ does are on the plane alpha I, alpha j, which is a complement to this thing. So here is my plane. This is where it goes bad when I fill this in. Okay. This thing right here is the span of alpha I and alpha j. Okay. So I'm basically saying that my action of Sij does nothing here, and it does something to this plane. Okay. This is what it does on the intersection of alpha I and alpha j perpendicular. And this is the interesting thing that it does to that brown plane. Okay. So now what? Let's figure out what the eigenvalues of this Si, Sj are. Okay. Well, first of all, here we have an n minus 2 dimensional plane that is fixed by Si, Sj. Okay. So I can just pick a basis for that n minus 2 dimensional thing, and I get n minus 2 linearly independent vectors which are fixed by S1, S2. So that means that S1, S2 has n minus 2 independent eigenvectors with eigenvalue 1. Where are they? Just take a basis for alpha I perp intersect alpha j perp. And it might have more actually, because this is but it has at least n minus 2. Okay. Where do the other two eigenvectors come from? Well, basically from whatever Si and Sj does here. Okay. These n minus 2 come from over here, and we just have to get the other two from here, which are basically the two eigenvalues of this matrix. And that means we can do 2 by 2 eigenvalues, which is kind of the only one that we might want to do by hand. So the other two eigenvalues come from this matrix right here. They are, let's call them lambda, and what's the other one? Well, look at this matrix. What's the determinant of this matrix? Actually, this is a minus 1. Huh? So this is 1 minus AB plus AB. It's 1. It has determinant 1. So if one eigenvalue is lambda, then the other eigenvalue has to be 1 over lambda, because the determinant is the product of the eigenvalues. Okay? Because this thing has determinant 1. Okay? So now, first let's suppose that Mij is finite. Okay. What does that mean? That means that Sij to the Mij is the identity, right? And in particular, that must mean that if I raise this matrix to the Mij power, I'm going to have to get the identity matrix. But let me put this in a different way. The eigenvalues of this matrix are lambda and 1 over lambda. Now, what happens to eigenvalues when you raise a matrix to the nth power? Remember? If you don't remember, this is a good exercise to do it. The eigenvalues of a to the m are lambda to the m. Sounds reasonable, surely. So if lambda is an eigenvalue of this matrix, then lambda to the Mij is an eigenvalue of this matrix. But we know the eigenvalues of this matrix. It's the identity matrix. So, yeah. It's the identity matrix, so 1. Okay. So then what can we say? Well, lambda has to be some root of unity. Right? And we know what these look like. E to the 2 pi I over Mij times k. Some k. Okay. Now this is lambda. What's 1 over lambda? Well, 1 over lambda is going to be the same thing with a minus sign here. So let me say that lambda and 1 over lambda are e to the plus this, e to the minus this. Okay. And so now I want to do the following. Basically, there's two possibilities. Either this is 1 or not 1. Okay. So let's do two cases. That these numbers are 1 and 1, or that there's some root of unity and the conjugate root of unity. So let's come here to the first case. So case 1 is that lambda and 1 over lambda are 1 and 1. Okay. So we have a 2 by 2 matrix, which is written over there. AB minus 1, B minus A minus 1. We have a 2 by 2 by 2 matrix, and the eigenvalues are 1 and 1. Okay? And now, so we remember from the linear algebra that there's two possibilities. Either you can diagonalize this matrix or you cannot. Remember, if you get different eigenvalues, then you automatically can diagonalize your matrix. And if you get equal eigenvalues, then you might have to deal with these generalized eigenvectors. That's how it works. So 1, suppose that this is diagonalizable. Okay. What does that mean? It means that we can find two more vectors, Si as j v1 equal to v1, Si as j of v2 equal to v2. Okay. For v1 and v2 in the span of alpha I and alpha j. Okay. And what do we conclude? Well, you see, over there we had already found n minus 2 linearly independent eigenvectors with lambda equals 1. And we just found two more, v1 and v2, which are linearly independent with them because these guys are in the span of alpha I and alpha j. The other guys are perpendicular to alpha I and alpha j. So with those n minus 2 eigenvectors and these 2 eigenvectors, we have found n linearly independent eigenvectors. Independent eigenvectors with eigenvalue 1. And that means that everything is an eigenvector with lambda equals 1, right? Because S1, S2 doesn't do anything to any of these eigenvectors. And these eigenvectors are n linearly independent things, so they are bases for the whole space. Okay? If S1, S2 doesn't do anything to an individual eigenvector, then it doesn't do anything to the whole space. Okay? So that means that S1, S2 is the identity. Okay. Sorry, Si, Sj is the identity. Okay. And if Sj, Sj is the identity, then Mij is the order of the identity, which is 1. And that leads us to a contradiction because we had assumed that Mij was greater than or equal to 3. So that means that case 1 cannot be. It can't be that these eigenvalues are 1 and 1. Case 2. Case 2 is that these things are actually given by e to the etc., which I want to write out. Like this. So this is what lambda and 1 over lambda are, okay? Where k is between Mij and 0. And now I eliminated the equality here because k cannot be 0. Because if k was 0, then it would be 1 plus 0. Okay. So we're supposing that lambda and 1 over lambda look like this. Okay? Now, here's a nice thing about this. Let's compute lambda plus 1 over lambda in 2 ways. Well, first of all, I can do it by just adding these two things and getting cosine plus I plus cosine minus I. So I get 2 cosine of 2 pi k over Mij. So that's what I get if I just plug into here. But what if I remind myself what lambda and 1 over lambda are? Lambda and 1 over lambda are the eigenvalues of this thing. And what happens when you add up the eigenvalues of a matrix? That's the trace. It's called the trace. And turns out that the trace can be computed very easily as adding up the diagonal. Okay. So that means that I know what lambda plus 1 over lambda is in a different way. Well, let me write it here. Let me explicitly write 2 linear algebra facts that I'm using here that you may have forgotten, and you should remind yourselves of. There's basically 2 ways of computing determinants and trace. One from the matrix, one from the eigenvalues. So from the matrix, the determinant you compute in kind of looking at, I mean, in this case, it's just this minus this. Right? But if you happen to know the eigenvalues, then all you have to do is multiply them and you get the determinant. For the trace, one way of computing it is adding up the diagonal. But if you happen to know the eigenvalues, then the trace is the sum of the eigenvalues. These are 2 key linear algebra facts that you see I'm using very importantly here. The thing is that now we can finally understand why this strange restriction is going to come up. Because if you look at this equation, these two look like things that should not be equal to each other, or it should be surprising that they're equal to each other. Why? Because this is some cosine times 2, but if you remember, a and b are integers. Okay? And so it should look very strange to you that some cosine multiplied by 2 is an integer. But that's what we just proved. Remember, it's key to remember that a and b are integers because they're the numbers that go in the matrix. That's how we define them. Okay? So by looking at the right-hand side, we know that this is an integer. By looking at the left-hand side, we know that there aren't that many possibilities for what this integer can be, because this number doesn't get so big. Cosine is between minus 1 and 1. So if this is going to be an integer, then there's only 5 possibilities. Minus 2. Look at how many possibilities there are in that table, by the way. If this is an integer and it's 2 times the cosine, then it has to be one of these guys. Okay? Okay. Now, could this be a 2? I want to narrow this down even further. I'm saying this could not be a 2. The reason this could not be a 2 is that if it was a 2, that means that this cosine would be a 1. And if this was a 1, if the cosine is 1, the sine has to be 0. And that means that lambda and 1 over lambda would be 1, which means we would be in this case over here. So this cannot be a 2 because lambda is not 1. So that case can't be. Okay. Now, could this be a minus 2? Well, let's try to repeat that argument. If this is a minus 2, that means that this cosine is a minus 1. That means that the eigenvalues are minus 1 and minus 1. That's not necessarily a contradiction. So we don't get a contradiction, but actually if you look at the other side, we do get a contradiction, because if this was a minus 2, that would mean that AB would have to be 0. AB is Aij, Aji. And we talked about the case 0 already. We showed that if Aij, Aji is 0, then Mij would be 2. Okay. In this case, Mij would be 2, but we assume that Mij is at least 3. Okay. And so that means that this number is minus 1, 0, or 1. Okay. So that means that the cosine of 2 pi k over Mij has to be equal to minus a half, or 0, or a half. Okay. And what are these the cosines of? What's the easiest? Cosine of what is 0? Pi over 2, right? Cosine of what is a half? Pi over 3. Cosine of what is minus 1/2? 2 pi over 3. Okay. Now look at this. Cosine of 2 pi integer over integer. Okay. So let me not write this as pi over 2, but as 2 pi over 4. Let me not write this as pi over 3, but as 2 pi over 6. Now, remember that k is between 0 and Mij. Okay. which means that actually this guy has to be either this or this or this. So what that means is that Mij has to be either 3 or 4 or 6, which is what I wanted to show. And not only that, but we know exactly when each one of these happens, because when do we get minus 1, 0, or 1 here? Well, according to whether this is AB minus 2. So this happens when AB is 1. This happens when AB is 2. This happens when AB is 3. So if AB is 1, I get that Mij is 3. If AB is 2, I get that Mij is 4. If AB is 3, I get that Mij is 6. And so that proves to me these equivalences. I think it's kind of magical how it just comes out of all of this stuff. So what I mean, it's very applied linear algebra, applied trigonometry. You would never guess when you're taking trigonometry that this is how you might end up applying it one day. Okay. What about? I made a big assumption here, which was that Mij is not infinite. Okay. I'm missing the case Mij infinite, and I want to just say a quick word about that. So what if Mij is infinite? Well, what I'm missing is I would need to prove that this number is at least 4, that it can't be 0, 1, 2, or 3. So let's suppose that it isn't. Let's suppose that AB is less than or equal to 3. Okay. So again, on alpha I perp intersect alpha j perp, Mij is the identity. And on span of alpha I and alpha j, the matrix is, well, it depends. I mean, it looks like this, right? And depending on what AB is, for example, well, we know that AB cannot be 0 because we already talked about the case AB equals 0, and we understood that for AB equals 0, we get order 2. So let's suppose that AB is 1, 2, or 3. So if AB is 1, that means that, and remember that they're negative, right? They're non-positive, so that means that they both have to be negative 1. Sorry. So what we get is 0, 1, minus 1, minus 1. In this case, what we get is 1, minus 1, 2, minus 1. And in this case, we get 2, minus 1, 3, minus 1. The point is, for example, if AB is 3 and they're both integers, there's not a lot of possibilities. They have to be 1 and 3. Okay, and you can choose which is which because you can just switch the roles of alpha I and alpha j. Okay, so that means that the eigenvalues here are 1, and now we just have to check what the eigenvalues of these three things are. Okay, and if you do it, you find that the eigenvalues of this one are e to the 2 pi, I mean, you just compute. You get that in this case they're this. I mean, you can guess what they are. In this case, you compute and you get that they're this. And in this case, you compute and you find that they're this, which you might not have guessed ahead of time you were going to get these answers. But when you think about them, that's the answers that you should get, because we saw there that you should be getting orders 3, 4, and 6. And that means here we get 3, 4, and 6. Okay. So in this case, the order of Mij is 3. In this case, the order Mij is 4. In this case, the order Mij is 6. And it's not infinity, as I assume, which discards this possibility. Which means that if you have infinite here, you have greater than or equal to 4 here. And proof it here. So there you have it. That's the beautiful theorem that tells you how to go from the Cartan matrix to the Coxeter matrix. And next time what we'll do is we'll actually construct root systems that realize each one of these things. So what I had drawn this picture for, this is one of my favorite crystallographic root systems. It's a nice root system. It's kind of good looking. And it's crystallographic. And so it would be a good exercise for you to look at it and see which one of these categories it falls in. All right.
Federico, your office hours are 2 today?
To what?
Yesterday?
To soccer?